Alessandra Cagnazzo from Eyer. Yeah. Anomaly detection in the real world.
Yes. Okay, I'm pretty excited to be here because I'm a former, forever mathematical theoretical physicist that used to be very formal and now is very applied. And this is my first time in 10 years talking about my stuff in front of my old crowd. And it's exciting, but I'm afraid that I will say something dumb because I've been so used in the past 10 years to talk about like my job at the general level, and now I'm in front of all these people that are so good to go in depth into things. And I talk about anomaly detection today, and I have to say that I am the anomaly today because this is a fantastic quantum computing day, but I do classical computing. Because I work for a startup. I founded a startup, and I mean, my mantra is to deliver something that gives me money. I have to develop a product, and we know that quantum computing is not quite there to give like fast development and fast return on investment right now. So I'll make this a bit like a story of my life, how I went from being a super formal person, taking pride in doing something that has no application whatsoever, to someone that actually delivers a commercial product. And so this is my path that, yeah, pretty linear. Okay, we know that it's a struggle academia, but it was pretty linear into academia. So doing all my PhD, my postdocs here and there. And then at a certain point, facing the choice, yeah, what do I do with my life? What is going to be my career? And in all that mess that happened here, I happened to be in Oslo at the time. And there's a startup lab. That is a lab for startups. Most of them are spin-off of the university. But the startup that I joined at the time was not a spin-off of what I was doing because superstring theory are not very startup-y material. But what happened, this was Ames was a startup that was a spin-off of the computer science department. And they had a lot of good developers, but not many mathematical people. And I met them, started to talk. I know algorithms, yeah? Do you know machine learning? I can learn. And machine learning was a very popular thing at the time. Somehow became less of a buzzword in the past couple of years, but it was what attracted money at the end of the day then. So I started to work with them, and I went into the field of anomaly detection for time series. So detecting if in a series of data points with a timestamp, there's something weird. And that has a very practical industrial application because there are a lot of companies that are willing to pay for us to analyze the data that they have, the pile of time series that they have from their IT systems. But as you see there, that was not the end of my journey because startup world goes up and down. And this company started to diverge from what I was doing. So at the time, I started to develop a prototype of a new product in the field of anomaly detection, but was not brought on. And with some of my colleagues at that time, we just said, you know what? We like this product. We really like this product. We are willing to invest our time and money into make this some startup, some idea. And that's what happened. That's how Eyer was born. And with these gentlemen here, we went into this startup adventure. I like to joke that we are like very old people for the startup world, because if you sum up all our ages, we go well above 200 years. So, but we started to work into to develop this new product. And right now, after 1.5 years, we are selling it. We have clients. We are doing proof of concept with some companies. So still very unsure, still very much money going out of my pocket, but it's a nice adventure that is shaping. So since it was not the main topic of the day, I just want to introduce some dictionary for what I'm going to talk about. And a lot of these things, probably you know, you have heard, have been hyped for the past 10 years. So most probably you have been seeing that also in the field of mathematics and physics have been studied at a more academic level. But I decided to pick up these words because of where the words that I learned after leaving academia. First of all, is machine learning. And there's a joke that all machine learning is linear or logistic regression. And that's indeed quite true if you look at it, because it's the paradigmatic example of machine learning, and it's still, at the application level, is still a useful algorithm. And of course, it's linear. So a lot of the machine learning boom came with like non-linearities coming into the game. And we have Gaussian processes, and here in the Gaussian processing part, you can find again ideas like the Hilbert space and Hilbert Gaussian processes. So these are all fields in which former people have been investing time researching. And of course, there's the field of neural network that just to simplify that, but that was how I understood neural network, like from day zero. Was like a convolution of linear functions, and then inserting no linearities here and there. Of course, this is a complex field, and there's a lot of formal debate that you can bring into this field, but none of that matters in my everyday life, because, yeah, what I do, it's something very, very applied, working with the client.
So for the table back,
yeah,
for the Gaussian process, what's the relation between Ka and the kernel KSX prime? The last line is why you put some Ka. These two are related. The Ka.
Yeah, this is. Yeah, I even don't remember very much of this stuff.
They are related.
Yeah, they are. It's a kernel that you basically.
That one's a kernel.
Yeah. It's basically the way that you have to go to a infinite dimensional space, and that's as far as I remember. Knew that I didn't have to put formulas in my talk because, but as far as I remember, that was the that is really much the way to not having to deal with that infinite dimensional space, and. Yeah, and going back, supervised and unsupervised learning. It's basically optimizing your function, because at the end of the day, what you want is a function that you use, and that stays true no matter what computation you are, quantum or non-quantum, you are into. And you want to optimize a function, and you can do it with or without examples. In my case, with or without someone saying that that is an anomaly. That was a problem. Because while having examples is great, training with examples is great, but it's not always possible. It's a time-consuming thing. It's a very tedious thing to do, and most of the companies are not really investing into that activity. So that's why in my company we have been focusing a lot with the unsupervised part, trying to extract value without having any example. Anything, our clients don't have the will, the time, the interest to tell us that was a problem, that was not a problem in our data. And that's, is anomaly detection, my field, and it's a huge, enormous field that actually I would like to know more about, because there's a lot of good research and academic research, but also a lot of times, I mean, is always the case, a lot of fantastic algorithms that are out there and beautiful and maybe giving even very good, precise results are not that easy or feasible when you talk to the real world. You talk to deliver something good to your client. So anomaly detection can be everything from like baselining 3 sigma of all the historical data that you had, and then you alert that you have an anomaly when it's outside the baseline, to autoregressive model is something that has been around for more than half a century, but it's still very much useful, and it's basically, instead of like doing a regression using 2 variables, x and y, you use the same variable but a previous timestamp. This is like the simpler model of all this one. And of course, there's also all the neural network world, so making this more and more complex, more and more precise. And an example of, like, in the unsupervised world is the example of autoencoders, and which are basically neural networks that have a compression layer, so dimensional reduction, like you would do principal component analysis, and you train them on a set of data, and then at the output you have like an error, of course, when you're reconstructing your data, and that when you are applying that to new data, if the error with the reconstructed data is bigger than a certain threshold, then you say that that is an anomaly. But all this is big, and not all this come at the same cost, because the cost of producing and calculating and training, which is the costly thing, a neural network, it can vary a lot. And in my case, cost, it really means cost out of my pocket. So my salary will be less if my algorithm is taking too much money to train. Okay, and this was the part of machine learning, but then there was also the part of computer science. And just one thing that is very important for what I do right now is the API. I didn't know what an API was when I started, but it's an application programming interface, and basically is really that layer that encodes and takes all the results of your analysis and deliver them to the user. And then the user can make requests and take out data from that. This is very important for my company right now, and it's and also, I mean, also of course gives a security layer there. You can put authentication and all these things. And finally is the hype of the moment. Maybe, of course, you already heard of generative AI, ChatGPT, LLMs, and all these things. And it's a bubble, probably. It's for sure more than something is going to stay. It's not something that completely will disappear, but it's also something that stakeholders, investors put a lot of trust right now in. And
can I ask if like next token prediction is related to what you were calling anomaly detection? Because it sounded like you were saying you've got some time sequence and you're trying to predict the next item, and if thing that happens is too far away from what you predicted, then it's an anomaly. It sounds a lot like saying you do next token prediction. If the next token is different from one that you were expecting to see.
Yeah, that's a type of anomaly. That's a type of anomaly detection that you can
Okay.
leverage.
Is it related to your approach, or?
It's the next token prediction. It's more like on NLP, so language processing and log processing, and point of view. It's what the core functionality that we have is numeric. So if you want to say like yes, prediction of the next numerical point
So
is
the sequence is a sequence of
real numbers. I mean, yeah, real numbers. So that's the main focus. But of course, it's not that we haven't experimented with all the part of next token prediction, NLP, and actually we also already in the previous company we started with like research projects in that area. It's not something that we offer to our clients today. Also because in that part right now there's also a bit of work that can be done from the point of view of this LLM. So it will come. But another thing that I wanted to mention is AI agents. That, from my point of view, is like the rebranding of what we had already is basically different pieces of code talking together, and the way that they talk together is often through the famous API that I mentioned before. So that's why it's so central also for my business, and this is something that like have been evolving in the last few years, but the approach of not having like a monolithic code, a monolithic thing doing all the tasks, and instead of having like a lot of specialized tools and things working together. I've been showing that that's the right approach for a lot of reasons, and also for computational stability and a lot of practical application. And also nowadays there are all these tools that came out, and you can build your own AI agent. Just drag all your different boxes doing different stuff, put them together, and voila, you add a chat or LLM model here and there, and then you have your hypermodal AI agent. And this is actually like an AI agent that is not part of my product, but it's just something that I built, leveraging a bit my product in probably half an hour or something like that. So that's the fun part. There are also building blocks out there to build stuff. So now to the slides that are taken from our investor deck, so the part that are a bit more businessy. And this is actually when we thought about Eyer, we didn't know that LLM and generative AI was coming. This was 3 or 4 years ago. But we decided probably it will pay off to go with this API approach, in which we don't invest our time into do some graphic user interface, and we just do really a computational engine that our clients can just take and plug in whatever they already have. So we just decided, okay, we have an API that is a layer to which our client can send the data, and there's then an API in which our client can just extract the result of the analysis in a very simplified way. But now this thing all of a sudden became quite interesting for everyone because this is naturally is an agent that integrates with a LLM. So a lot of like the promoting, but also a lot of like the feedback that we have from people is like, oh yeah, that's cool. I want to integrate that with the LLM, but make it part of the effort that we have to have generative AI into our ecosystem. Okay, this is like the very core functionality that we offer once you send in the data. So it's baselining and anomaly detection based on that baselining, and then correlation among time series, and then consolidating all the anomalies that we see and correlation together to deliver a single alert of all the anomalies that we see that are correlated. This becomes quite important because probably I have to mention that our target is not like the company that has 5 time series to analyze. It's the company that has hundreds, thousands of time series to analyze. So not a company that is not some job that it would be easy or feasible to do manually, or even that is so easy to do if you don't have a team of in-house data engineers, data scientists that work for your company. This is, I want just to go through a bit of like the challenges, also the what I had to compromise by going into this, because okay, we have no labeled training data, so we just can do unsupervised learning stuff. In the end, we end up using, instead of like a monolithic, like big neural network, we end up using a mixture of different lighter weight algorithms. And this is, like for example, for a correlation, we prefer to do linear correlation as much as possible. And this has 2 main reasons. First of all, simpler algorithms are easier to interpret. So for once you have an alert saying, oh, something is going on in my system, you can actually understand, if you take the time to do that, you can understand why that that alert was created, and this is not always easy with more complex, very complex neural network algorithms. And also the interplay between my algorithm and the architecture, it's very important. We do close to real-time anomaly detection, so there can be some delay, but we have to have something that runs fast and is stable and delivers the results in a timely manner. There are a lot of architecture and technical challenges with streaming the data live to the client and all these things. So you cannot make it fancy from the point of view of the algorithm. And but this pays off at the end, because we managed to have something that is reliable for our client. And okay, these are just plots of like all the nice shiny things that you can do if you use a visualization tool that is external to our company, because we don't provide an UI. Yeah. Of course, I have the integration with ChatGPT or Claude in this case, asking, oh, what's going on? Do I have any anomalies today in my system? And yeah, that that's maybe a easier way to interact for non-very technical people, but that also has like a quite nice application. That is the fact that actually all these LLM, they are pretty good into digging into your log system and documentation. So if you have an anomaly and you ask them what was happening in the logs there, or what does my documentation say about that particular resource that I have an anomaly from, you get an answer pretty quickly. And we have to remember that a lot of these companies have a humongous documentation that no one takes the time to really read. So that's where actually these things can become really useful. And then my personal conclusion, and then I realized that this is the first time that I give a talk here or like anywhere else in mathematics in which I don't have a slide that says conclusions. It's really a bit different, and we basically use what works. We have to use what works in our product. A truth that I learned is that a lot of the anomalies of our clients are trivial. It's like they want to be alerted if they have like CPU memory that is usually 5%, and then all of a sudden is 30%. And yeah, that's kind of a trivial anomaly. Or missing data. That is another type of rather trivial thing to discover. And the main complication that we have is the high dimensionality. So, and the real-time complication that we have. Enlightenment models are more stable over time. They don't need to be retrained so often. They will miss nuances, but also one has to bear in mind that, okay, we are analyzing a lot of different aspects, a lot of different time series coming from the same resource, probably. So detecting an anomaly in half of them is good enough. It's not that I have to detect an anomaly in all of them. This thing that the less your model is complex and hyper-trained and overfitted, the least is the chance that you have to retrain it. And also now probably all of you heard about the cloud, but now when you want to write a computer program or whatever, you can just go into a cloud provider and add your resources. I add a virtual machine here, and then we get like a storage in there, and you can do it like in 1 second, and things are very dynamical. So, like models need to be adaptable in a kind of modular way and a, scalable way. And this is a bit also, the thing where like the duck-sized horses are very important in my job, because we have this modularity of all the tiny algorithms that we have. And training a neural network is always time-consuming. Typically needs either labeled data, but also unsupervised learning neural network. They are still time-consuming and heavy and costly. So these are all the things that I had to compromise. And that is my last slide, and is a bit, I tried to kind of reconnect to the main topic of today. But it's really where I say a theoretical physicist, but because from my point of view, a theoretical physicist or mathematician or whatever can shine, and it's very important. It's really, there's the challenge now to make computation more efficient. And this is what often you hear, this will be solved by quantum computing, because quantum computing will make everything more efficient and the calculation will go faster and all these things. And that's also a way to think about it. But we know that it's not like behind the corner. It's not that we'll have like a industrial application tomorrow. But there's another thing in which like quantum, like theoretical physicists can get very good. It's like selecting a proper model. Selecting a model that has the right complexity for the problem that you are trying to solve. Because people like us, academics inclined to know a bit better the models, have to rarely, never use a model or an algorithm without knowing what that algorithm is or what that algorithm does. So we can really be sure that we don't use a black box when we go into an algorithm. And this is actually as a consequence in really the sustainability of your modeling and on your development. So yeah, optimizing machine learning in a lot of cases can be done by using simpler models, or yeah, going quantum. Keep with the good job and you will go there, but of course probably you will also need a problem that thrives into the quantum to be solved with the quantum. Okay.
Thank you very much. This is an anomalous talk, and also anticipating maybe even the discussion session, the panel. Are there questions or comments? Now, in your previous slide, you seem to have actually also highlighted something on which one might, I don't know if you can identify a way in which some theoretician could help dimensionality real time, but that's all has to do with efficiency. Sorry, I'm a bit ignorant about the subject, but when you talk about a main complication to be dimensionality of the systems and real-time problem, is there something that can be written down as a problem to solve in more details than?
I don't know if you really, if I understand what you mean. Of course, it's not like a dimensionality problem like for us, us for, but yeah, the problem, yeah, sorry. One thing that it's also reconnected to what I'm not able to answer to him, but it's really the fact that here you kind of end up in a base that is infinite, and in general, like the feature space, let's call it, like of these clients, if you work in that base that they are, which the data are collected, it's big. It's hundreds of thousands of time series. So of course, there's also a job like rotations and transformations and dimensional reductions, and that is a theoretical field that can come and help to rescue.
Thanks for the comment. And so machine learning, again, maybe dumb person, is, I understood it's more an opportunity, like more than a threatening for your activity.
Yeah, definitely. I mean, this is
true.
This is a very good question, also from like maybe a political point of view, but depends on what you mean by machine learning. It's the machine learning per se, like all the field, all the chances, computational improvement, GPUs, and all these things, they are immense help to build whatever. Also, just thinking about the fact that there are like a lot of packages out there that can be reused and all these things. So it's really a big chance. If you say machine learning and what is considered and perceived by the public as machine learning, like this new, and I'm talking mostly about generative AI now because it's like what is popular and right now. That can be a threat, but not because they can do my job, because really my job is to do something mathematically sound that the LLM then can use and present the analysis of. But they can be a threat because people might think that they can do my job. And this will fire back to those companies that will now are firing or downsizing and thinking that generative AI is going to solve everything. So yeah, maybe from a funding point of view, yeah, they could be a threat.
Very good for the comments. We continue in the panel, perhaps. But for the moment, let us thank Alessandra again.